Okay. Did that go away? So let's think about what the effect of the first and second derivative are doing. So the key points we looked at last lesson were, okay, we've got a first derivative at some point equals 0, they're stationary points. But then we evaluate the second derivative at that point, and we're looking for it to be either greater than or less than. So who remembers what that they are indicating?
Minimum.
Yep. So greater than, it takes that shape, becomes a local minimum. Less than, it becomes a local maximum. Okay. But however, if it equals 0, then it says we're going to investigate further. So particularly, what do we want to consider when we get this scenario, when we get the second derivative actually equals 0, and we investigate further to think about what's the point looking like? What are the two possibilities we could be considering? Point of inflection or a stationary point of inflection. So if then the first derivative at that point is also equal to 0, what does that suggest? Stationary point of inflection. Yep. But if it's not 0, then it's just a point of inflection, and then those features, the one on the graph will come down, it will go flat at that point, so it's stationary. And then this other one is where we've got some kind of maximum gradient point here. Somewhere in the middle, where it's maximum gradient, maximum steepness. There's the two scenarios we're after. Okay, so another good thing to consider is hiding. If we have a function, we want to examine the three graphs of this function. The function itself, its derivative, and its second derivative. So let's look at all three versions of the graph side by side. Okay, so this is a fairly simple cubic. So just have a think about what that might look like by hand. All right. So considering you have three graphs now, what's the coincidence of your main features? So here in your on your f of x function, you've got your stationary points. There and down here. Now those stationary points on your gradient function, where do they coincide? What's the feature you see on the gradient function sketch? It will be the actual intercept, that's correct. So you can see the stationary points on your function is down here at x equals 0 and another one at x equals 10. Yeah? And so now those become intercepts on the gradient function graph. Okay? Stationary points. That point there, that one down there, and they also are appearing here and there. Now you don't see stationary points on the second derivative anymore. There's no coinciding feature, for instance. Okay, but the second derivative is indicating locating a different feature. Okay, such that if you look now at a stationary point on the gradient function, being this point there, this stationary point on the gradient function is a stationary point of the rate of change. Yeah? All right, now where's that appearing on the double derivative graph? That's here on the x-axis intercept, that same point there. Okay, so the third graph is simply a rate of change of the gradient graph, our f dash. Yeah? And so the same thinking applies. If you've got a stationary point or a turning point on the gradient graph, that's going to be equaling 0, or 0 point, or x-axis intercept on the double derivative graph. Okay, so it says find the value of x for which the gradient is a maximum. So where do we see where the gradient is going to be a maximum? So we've got over here, we've recognized the point in the middle between the two stationary points is our max gradient. Right, and that appears over here as the x-axis intercept of the double derivative. All right, so that there is your coinciding max gradient. Location. All right, so you let your double derivative equal 0, and you solve that for x, essentially finding what's the x-axis intercept of that f dash dash function. So, what should that become? 10 on 3, is it? Well, if we had so that was the function there. We can see the gradient function is, first off, you can treat it as an expansion, and you get 10x squared minus x cubed. So what should be the gradient function? Yep, so multiply the 2 out. 20x minus 3x squared. Okay, and then the second derivative, that one's going to give you your stationary points when that equates to 0. All right. Then the second derivative goes to 20 minus 6x. Okay, and then this gives you max or min gradient. Okay, so if we do that, let it equal to 0. 20 minus 6x is equal to 0. X is then 10 on 3. Okay, now how do we know if we didn't have the graphs, for instance, and we just had working with the equation, what can we do to, in fact, help us figure out if this is a maximum gradient or a minimum gradient? That is just giving us a location. But is that going to be the location for a maximum or a minimum?
Yeah.
Yep, so solve for when the double derivative equals 0. That gives you the location first. And then what else could we use then to suggest if it's going to be a maximum value or a minimum value? Which one? 10 on 3 into which function? The derivative. Yep. Okay, so if we now, because we're talking about a gradient, we want to use the gradient function to figure out if we're going to get a maximum gradient number or a minimum gradient number. So sub x equals 10 on 3 into f dash.
What's the point minimum?
Okay, so it's 20, 10 on 3 minus 3, 10 on 3 squared. Now what are we looking for when we're evaluating such a number?
Positive one.
Positive or negative? Very good. So what we're getting is a 200 on 3 minus, now what does that give you?
Positive.
100 on 9, 300 on 9, or 100 on 3. So from that we can determine that must be positive.
Wait, it's negative.
Becomes positive, doesn't it? So being positive gradient, that must be a maximum. Maximum values are positive values. Okay, so the minimum gradient, the most minimum gradient would have to be the most negative gradient that you're looking for. Okay, such that your shape just comes up like that, climbs, and goes down.
Yeah. Yeah.
It's this point there. Okay. So you can see it's the most positive steepest gradient. So it's the maximum gradient number. Okay. Yes.
If it's greater than 0, then it has to be the minimum point of inflection, right?
Look, if this one, in terms of thinking about the nature of the points of inflection, not a stationary point, not the nature of a stationary point, but the nature of a point of inflection, whether it's a maximum rate of change or a minimum rate of change, okay, you want to recognize that all maximum rates of change would be positive rates of change, okay, such that the point of inflection has this kind of shape, and when it's on an increasing function, like so, when it's increasing coming up, there's going to be a point in between those two stationary points where you've got the most largest positive gradient, all right? That would be regarded as a maximum gradient or maximum rate of change. Okay, that will be the largest positive.
To find that, we do it first.
So to recognize that, you just want to recognize you got a positive gradient. So substituting into our gradient function to see that it becomes positive would be an indicator that what we found is the maximum gradient. Does that make sense?
A must be a positive gradient, maximum positive gradient, or so the maximum gradients are positive and minimum gradients are negative.
That's correct. The minimum gradient would be the other way around, for instance. So if our turning point comes down, and that down here is a turning point, then in other words, there's going to be another point here somewhere in between those two turning points, such that it's got the steepest negative gradient. So m is less than 0. That's the most negative you can get. Okay, so being a negative number, negatives are smaller than positive numbers, so you regard that as the most minimum gradient or most minimum rate of change. Okay, so if you are recognizing substituting into our gradient function, yeah, and it becomes less than 0, negative gradient, then that's the minimum rate of change. Because what is the derivative, f dash, what is it determining about the curve? Not just the stationary points. Could be at any point you're getting the gradient of the curve. Yeah, you get the how steep a tangent would be. That's what f dash is giving us. Each gradient is determined by the gradient function. Yeah? And so based on that, if our gradient function is positive, then that would have to be, at this point of inflection. Being a point of inflection, okay, these are